We only have so far two people on the room. Let's wait a little bit more. I'll get some water. I'll be right back. We only have so far two people on the room. Let's wait a little bit more. Okay, everybody. I guess this is the four of us today. So let's start the seminars. Good morning. Uh, I'm sorry. I apologize for this past last week. I could not attend, and I hope we can replace this day on the next week. So today is the day where we are going to discuss quantum computation. We'll begin exactly quantum computation algorithms, and this would be a very important seminar. Okay, more people arriving. Yeah. So we'll do today. Let's first maybe discuss this the replenishing, so the substitution of previous day. I thought we could use the Thursday of the next week after the last seminar. So the last seminar was supposed to be on 6th of June. and maybe we could just continue and have the last seminar. So my idea was to do this seminar optional. Okay, so who cannot attend, I will not exactly discuss the key points of this course, because exactly the key points of the course will end on this day, on this last day here, D4, where we'll talk about junctions and so on. Okay, one more person. Good. And I think we can continue on this day if it's okay. What do you guys think? Uh, can we move the day we missed for this day? So maybe you guys can discuss with Valeria if there is some problems with this, but I guess it will be okay. Um, but today is about quantum computation. Let's give continuation. Okay, seems fine, right? Good, good. So today we continue with this quantum computation, quantum logic gates. So it's been almost 1 month since our last seminar. So I decided to do some review. So first I will start with some review of the concept of qubit, okay? Because I guess you guys already forgot, right? There will be many important concepts. We need to review this stuff. Then we go for new material. We'll go for some circuit models for making quantum computations using gates. Okay, again, the concept of gate will be very important. So it can be single qubit or double qubit, or and so on and so forth. So multiple qubits. Okay, and we'll study this very important concept of entanglement, and then go for more advanced stuff. Okay, so this is our plan for today. I hope we can move okay through this. So to begin with, let's remember this concept of qubit. Okay, so classical bit, again, something that is just 0, 1, right? Can exist in two distinct states. Um, like a single binary digit. Binary, right? Two, so either 0 or 1. But in contrast, a quantum qubit, quantum bit or qubit, the two-level quantum system described by a two-dimensional complex Hilbert space. And again, this is very technical. We don't need to go deep into this, but Hilbert space is the space where these states live. So this state, let's call this the ground state or the zero state. These are states that are part of this space. Okay, so this Hilbert space is the space where all these quantum states live inside. And we're not going through the deep mathematics of these spaces and so on. This is for more for mathematicians. But the point is that these functions which represent our state. Previously, in the classical computation, it was just binary functions, 0 or 1. And now, in the quantum bits, they will be made by superpositions of 0 and 1s, right? We saw on the previous lecture that in the quantum nature, you can be in sometimes in a uncertain state where there are only probabilities of being in one state, probabilities of being in another state, and you need to make measurement and define which state that system is, right? So now we are going for quantum world, right? And so as I was talking, these two states, they form a computational basis. So the basis where you can just build all the other states by doing linear combinations. So if you take coefficients in front of both of these vectors and sum them, or vectors or states, right? And sum them, you will build a more general state. So here, this alpha and betas, they can be complex numbers. And when you make a combination with both these states, you can have a more general state, right? So it can be I, can be 1, 0, minus I, e to, can be anything, right? E to power something, e to power phi. So all these factors here can be like this, with the only one condition, that they obey the normalization condition. So normalization, the norm, I think all you guys know, right? The norm of the vector. When you make, you have a vector v, and you take inner product with itself, you have the norm of this number, right? Or in complex numbers also, if you have a complex number z, and you take the norm of this complex number, this will be the real part squared plus imaginary part squared. So they have some kind of parallel between, there is even a mathematical mapping between the complex numbers and the 2D vectors, 2D real vectors, okay? So, but what about normalization? So normalization condition is that the norm of this vector is 1, which means that if we go to this probabilistic interpretation of the wave function, it means that you will always find one particle there. There is the probability that the state is in, the particle is in state 0, or the particle is in state 1, or the quantum system in general, it is in space 0, or the quantum system is in space, in state 1. But because of probability theory, we need to have all the possible combinations. When you sum all these probabilities, they should give 100%, or they should give 1. So this is the normalization condition. Okay? Everything clear? I hope I did not make even more complicated than what it is. But okay. So since the state vectors are defined only up to a global phase of no significance, I will explain this, what it means. One may choose a real and positive, um, except for the base state 1, in which alpha equal to 0, and one may take beta equal to 1 real. So what I'm talking? What I'm talking is that in principle, these numbers here, this is a number, right? And this is a number. But if you look, cosine of theta, this is real number. So we are deliberately choosing a global phase from these two, between these two numbers, between alpha and beta, right? Because if you remember, this was alpha, this was beta. This was the number that multiplied 1. So if you choose a global phase in which alpha is real, it means that you are actually subtracting the phase of some arbitrary complex number that you should have. Let's say in the beginning you had alpha equals some complex number, right? Let's call this norm modulus of alpha e to I phase of alpha, right? So if I just remove this phase from the whole number, so let's say I make e to minus I phase of alpha times psi. It means that this will be misunderstood. Misunderstood. Wait, someone wants to join this call. Let me. Ah, the name is misunderstood. I thought someone did not understand what I was talking. So misunderstood. Okay. So E2, let's remove this global phase. So it means that what we are going to have is actually norm of alpha times the state 0 plus beta times e to minus I phase of alpha times 1. So in this new configuration now, in this new state psi, what happens is that this entry, this number that multiplies 0 is a real number for sure, right? Because the modulus is a real number, right? And this changing phase doesn't change the amplitude of the quantum state, because when you make uh, the inner product between these vectors, what you have is that you have plus I to phi alpha times e to minus I phi alpha times psi. So this phase factor cancel with this phase factor, and this will be equals to the same thing, psi, psi. Okay, so changing the global phase doesn't change the amplitudes of the inner products. Okay, so we have this freedom. Because we have this freedom, we choose what is typically done is we choose the first number real. We choose this guy real, and this is a very clever map that we are doing here. So in this definition, we are taking, because of this condition, modulus of alpha squared plus modulus of beta squared equal to 1. This remembers cosines and sines, right? Because if you remember the fundamental theorem, this is some angle, let's say not theta to be, not to be unfortunate, but some angle, I don't know, z, sine squared of z plus cosine squared of z equals 1, right? This is fundamental theorem. And then this reminds of this condition, the normalization condition. So what we are cleverly doing here, we are already choosing some mapping where the amplitudes will be defined by angles. Okay, so we'll have this cosine, sine. Okay, and when we do modulus squared, this e to I phi goes away, disappears, right? And then we just have sine squared plus cosine squared. Instead of zeta, we choose theta over 2 for reasons that will be clear when you think about what mapping you want to get. So when you do your definitions like this, from with theta from 0 to pi and phi from 0 to 2 pi, you get exactly this so-called, where is it, the Bloch sphere, right? So we saw this, that psi in the end is just, don't worry, I will go back, but psi is just, if you think of a 3D spherical coordinates, right? And you think that in spherical coordinates you have radius, you have the azimuthal angle, and you have the polar angle, right? So let's choose the modulus 1, the radius 1 in spherical coordinates. So you have a sphere, and what you can change in this surface of sphere, you just have these two angles, theta and phi. Okay, so this is exactly the mapping we chose, is exactly the map of the sphere, okay, of radius 1. And then this was very clever mapping done by Bloch. And so therefore, unlike the classical bit, which you can have only zeros and ones, the qubit lives or resides in a vector space parameterized by continuous variables alpha and beta, or theta and phi. We just chose it very cleverly. Instead of alpha and beta, we chose theta and phi, because we can think of this state as being some vector on the surface of a sphere with radius 1. Okay, so in this case, a continuum of states are allowed, or is allowed. This contradicts our classical way of thinking. According to our intuition, a system with two states can only be in one state or another, right? So it is either 0 or 1, or as we say in Brazil, is either 8 or 80. But in the quantum state, no, it can be superpositions, and you can have actually infinite states, right? But at this stage, one might be tempted to say that a single qubit could be used to store an infinite amount of information, because it's infinite, it's a continuum of states, right? So if you can attach each angle to a point of information, you could think that your register could have infinite, right? But actually, we must in general provide infinitely many bits to specify a complex number, alpha and beta. But the catch is, to extract this information, we must perform a measurement. And quantum mechanics tells us that for the measurement of the state 0 or 1 of the qubit or plus or minus. We obtain only a single bit of information, plus or minus. So for the problem is the measurement. It's not the information you store, is how much information can you get from measuring. That's what's the limitation in quantum computation. Okay, we'll see this. So two-level quantum system can be used in practice as a qubit if it is possible to manipulate it as follows. So we have to be able to make transformations in this qubit, right? So it can be prepared in some well-defined state, for example, the state 0, which we can call the fiducial state of the qubit. Okay, so that's the trustworthy state. That's the state with lowest energy. Okay, you can safely determine this state. Okay, this is condition 1. Condition 2, any state of the qubit can be transformed into another state. So such transformations are carried out by means of unitary transformations, as we will see further in the next seminar, which will be today's seminar. The qubit state can be measured in computational basis, right? 0 and 1. That's it, right? So let's begin looking at these operators. So we have so far states, and we know that in states you can apply operators. So operators in general, they mean that it's some gate that you are passing your state through. So you pass this state through some gate. We saw in the last seminar, for example, you have a beam of atoms with spin up or down, and you put some magnetic field, and this magnetic field, inhomogeneous magnetic field, it will select states with spin up in some direction, states with spin down in the opposite direction, and then you will separate these two states, right? So that's what we can, for example, do, right? So if you prepare the state in already with spin up and you put in this gradient of field, what will happen is that all the atoms in this beam will go up. If you prepare in the state down, all the atoms in the beam will go down. So let's look at this transformation. This transformation usually are represented by Hermitian operators. So Hermitian operators are in complex numbers, in complex operators. These operators are symmetric, and they are what we call self-adjoint. You can take the complex conjugate actually, and you can transpose them. They will be the same. When you take the complex conjugate and transpose them, you get the same operator. These are so-called Hermitian operators. Okay. So for example, let's take an example. We will go for the Pauli operator sigma z, and it has states 0 and 1. This is a typo, by the way. No, 1 and -1 eigenstates. This is a typo here. I have to remember -1 and 1. The eigenstates. No, the eigenvalues are -1 and 1, and eigenstates are I like this 0 and 1. Anyway, let's look what I mean here. If the state of the qubit is described like this by psi equals cosine of theta over 2 plus I phi sine theta over 2, you get in vector representation something like this, right? Cosine of theta and e to I phi sine theta and so on. So as a result of the measurement, you can obtain 0 or 1 with such probabilities. So P0 is like this, and P1 is like this. Okay, so we are taking the eigenstates of sigma z, making the inner product with psi. So here can go either 0 or can go 1 psi. When you make this inner products, what you have when you take a modulus squared, what you have will be the probability squared of having the state in that state, having the system in that state. Okay, so let's call this P0. So this is equal to cosine square of theta over 2, and P1 is sine squared. You already see that we only have two states in the system. If you sum the probability 0 with probability 1, this gives 1. It means that statistically speaking, this is sound. The theory is sound. The theory is okay, right? Yeah. So this is the Bloch sphere. We constructed in a way that these angles will be exactly the polar coordinates, and then we can represent our quantum state in terms of the vector on the surface of this sphere with radius 1, right? So again, let's look at the Pauli operators and how they act on the basis vectors. Again, we saw this last time, but I think this is so complicated that we need to review this and to have a clear idea of what was done, because it's a lot of little details that we need to remember, right? So these Pauli operators, again, remember that sigma x is like this, sigma y is like this, sigma z is like this. Let's see how they act on the state psi. So sigma x on psi, what sigma does, it just exchanges x for y. So sigma x, let's say we have a vector x and y, and let's see what sigma x does to this vector. So you just have to perform some matrix product like this, 0 1 1 0 times x and y. So what you get is the opposite, the flipped, we call this the flipped vector. So this, you get yx as vector. So in the beginning you had x and y. What you have in the end is yx. Okay. So what it does to the vector psi, to the abstract vector psi, what it does, it exchanges this component that used to be in front of 1, it goes to 0, and this component, that this factor that used to be in front of 0, goes to 1. Okay, and same thing with the other operators. So sigma y is the same thing, it flips the vectors, but with opposite sign and multiplied by I. So basically it introduces a general phase in the state, because you will have now in front of 0, you will have a complex number, you will have this guy, and here you have a complex number, you have this guy. Again, we saw that multiplying by a complex number here will not change the modulus, right? The inner product. So this is not so serious. And sigma z, what it does, it just changes sign on the last component, on the component of the vector 1. So here it used to be plus, and now it's 0 after you apply sigma z, right? So same thing, you just multiply by it, almost diagonal matrix. No, this is a diagonal matrix, but it's almost the identity matrix. The only difference is that you have this minus sign, right? Okay, this is the action of the Pauli matrices on an arbitrary vector divided into these components, right? So now let's look at the expectation values of these matrices. So now sigma psi, and we make inner product with psi, or in other language you can also call this a contraction. So a contraction means that before you had something with higher dimensions, and it becomes something with a number. It becomes a number in the end. This is sometimes called contraction. Okay. But yeah, so let's call this inner product. So psi sigma x psi will be this inner product here. You guys can make yourselves and verify that what you will have will be the components, the Cartesian components of this vector. So we mapped our quantum state in terms of theta and phi, but when you apply the Pauli matrices on psi, the expected values, so when you put this operator in the middle of this sandwich, so to say, of vectors, what you get are the Cartesian components, x, y, z. So I don't know, maybe I could do 1, 2 as an example. Let me check when is our break, because maybe time is flying too fast. No, we have time. Yeah. So for example, psi sigma x psi, right, can be something like this. We saw the action before of sigma x psi, right? Right? We saw that this is sine theta over 2 e to I phi minus complex conjugate sine theta over 2. This is this dual vector, and we are going to make inner product with the action of this operator on psi, so sigma x on psi. As we saw, it just exchanges the components. So what we have here is just e to I phi sine of theta over 2. And here we have, oh, sorry, I'm making a mistake. Yeah, so it will be a vector like this. It will be actually e to I phi sine theta over 2. And here will be cosine theta over 2. So this is the dual vector, this guy. And this is the action of the operator on, okay, action of the operator on the state vector. So what we will have here will be e to I phi sine theta over 2 cosine theta over 2 plus e to minus I phi sine of theta over 2 cosine theta over 2. So what we have here, we have, if these are two complex numbers that you are summing, these are the complex conjugate of each other, because the phase factor here is plus I phi and minus I phi. So when you sum a complex number with its complex conjugate, what you have is twice the real part, right? Yeah, twice the real part. So we have 2 times cosine phi. Wait, sorry. 2 times cosine phi times 1/2. And then you can use this trigonometric identity, sine of theta, cosine of theta. This is 1/2 of the sine of the double. So this would be sine of theta. Here we have theta over 2, and then the double becomes theta. So 2 cuts with 2. You have cosine phi sine theta, this result here that we have. And in spherical coordinates, sine theta cosine phi, this is exactly x. You can see this on the Bloch sphere. So if you have this vector here, and you can take this projection to the horizontal plane. So this projection here, the size of this projection, here let's put the size of this projection. Okay, so this is sine of, wait a minute, sine of theta. Yes, sine of theta times, if you want the x component, then you need to take this component. Oh my god, this drawing is so bad, I'm sorry, but it's too small, right, to see. But you have to take first the horizontal component, which will be sine theta, and then you have to take the component of the component. So that will be sine theta times cosine phi. This will be x. If you want y, it will be sine theta sine phi. And if you want z, it will be just cosine theta. So as you can see from the actions of the Bloch sphere, this is exactly what we have here. So the x component will be sine theta cosine phi, the y component will be sine theta sine phi, and the z component will be cosine phi. Okay, this could be a good calculations. You can do yourself at home. It's quite maybe this is obvious for some of you, but you can check this yourself. It's quite simple. Okay, and these coordinates x, y, and z can be obtained with arbitrary accuracy by means of the standard projective measurements on the computational basis. That is measuring sigma z. Okay, so what I mean by here. So if you take the probability of having being the state 0, subtract by the probability of being on the state 1. Then let me translate this into the real world phrase. You will have this thing, cosine of squared of theta over 2 minus sine squared of theta over 2. This is by trigonometric identity. This is cosine theta, and this gives z, right? So if you look in the Bloch sphere, this gives exactly an interpretation. So if you have your vector psi with some component in the z direction here, right? Let's call this component of this vector in the z direction. This is exactly the probability the difference of probability of finding this vector in state z, in state 0. So for example here, if we call this the state 0, and if being low here is the state 1, so the bigger the positive and bigger z, you are closer to the state 0. The smaller and negative z, you are closer to the state 1. Okay, so this sphere even have this interpretation that wherever you are in the sphere, you might be closer and closer to some pure state. Okay, 0 and 1. This is what I mean here. So standard projective measurements is just taking the projection. What I meant here is just taking the projection in the z direction, in the x direction, in the y direction, right? And the computational basis is 0 and 1, right? This is computational base, this couple of vectors, right? So if you subtract this p0 minus p1, you will have this cosine theta, and this will be z. So the difference in probability of finding who is more likely to be will be a component of the vector in the Bloch sphere. This is quite interesting result. I hope I didn't mess up much. If you have some questions, please just type and we can discuss. Okay, or maybe write or say something. I don't know. Okay, so the coordinate z is given by the difference, right, of probabilities to have 0, 1. And now this is the one of the main points also. If we have at our disposal a large number n of systems identically prepared in the state psi, we can infer z as n0 over n minus n1 over n, where n0 and n1 count the number of outcomes 0 and 1. What I mean here is that you are going to prepare a lot of experiments, repeat this experiment many times in the same conditions, right? And they will be, for example, this gas of atoms, very hot gas of silver, for example. And this hot gas the atoms can go either up or down, right? It will be shooting hot atoms of silver that can go up or down depending on the spin of the valence electron, the last electron in the atom. So and you start counting. So if one atom goes up, you count +1 and 0. If one atom goes down, you count this. So let's see, we have some question. If it turns out that a given matrix allows us to move, sorry, that the given matrix allows us to move from one coordinate system to another. Yeah, more or less. The idea here is that there are these two coordinate systems, as you told, right? There's the coordinate system with theta and phi with these angles, and there's one coordinate system x, y, z, right? And there's a mapping between both of them. And indeed, as you told, these operators, these matrices here, when you make this measurement, so when you make these sandwiches with the vectors, right, psi, and the make operator in the middle, when you do this stuff, you get precisely the Cartesian components, right? You get x, y, and z. Yeah. So indeed, this is. I think you got it right. Very good. Very good. So there is a mapping between Cartesian coordinates. But the point is that Cartesian coordinates, we have three entries, x, y, z, right? And this system, it can be simplified. It can be simplified to two coordinates, theta and phi. So that's the magic here that we did, is that if you say that your modulus is 1, you simplify your system to a sphere. So now what should be a 3D thing, 3D entity, now became 2D entity. You are on the surface of the sphere. Okay? Okay. And so going back, right? So if we start making a lot of measurements of the spin of the atoms and start counting, after many experiments, these numbers will stabilize. So this proportion will stabilize. So it will go, some percentage will be n0, some percentage will be n1, and you can take these components, exactly this difference, n0 over n minus n1 over n will give you the z component in the Bloch sphere. So this difference will give you exactly how close you are from the z equal to 1 or z equal to minus 1, or how close you are from the 0 state or how close you are from the 1 state. Okay. Usually, if this is completely random, for example, this Stern-Geller experiment where you have the atoms going up or atoms going down, usually if this is completely random, you just have 50-50, right? So in infinite counts, what you have is that n0 over n will go to 0.5 and n1 over n will go to 0.5. When you make 0.5 minus 0.5, you get 0. So actually, for completely random atoms, your vector is in the center, in the equator of the sphere. Okay. All right. I think somewhere here I have a home assignment. So what I did here was let's see. So the coordinates x and y can be obtained by using the possibility to operate a unitary transformation on the qubit. The unitary transformation described by the matrix, let's call this U3. Okay, it will be clear why U3. U3 equals 1 over square root of 2, 1, 1 minus 1, 1. Why is this called unitary matrix? Because when you do U transposed times U, you get the identity matrix. Okay, so this is U matrix. Usually, these matrices are related to rotations. Okay, usually unitary matrices represent rotations. And this is very natural because we are on the surface of a sphere. It means that we can rotate. If you remember, I think in somewhere in the school or maybe in basic mathematics in university, I'm not sure if this is in the case in Russia, but rotation matrices, they are represented like this. They are cosine theta, sine theta, minus sine theta, cosine theta. They are represented like this, rotation matrices. It means that you had, let's say you have a 2D vector like this, 2D vector V. And after you apply this rotation on V, what you have a rotation. This will be like V prime. Let's call this V prime equals U times V. So rotation applied on V. It means you rotated your vector on the angle theta. Okay. So maybe you guys saw this. If not, this is rotation operators in 2D. So usually unitary operators, they are represented like this. For example, in this case here we have 1 over square root of 2 and plus minus. So who has sines and cosines 1 over square root of 2? It's 45 degrees, right? So this U3 here is just a rotation matrix of 45 degrees. Okay? So if you have some state psi, after you apply U3 on psi, you will get, let's say, psi 3. It means that this is just rotation of 45 degrees on the vector psi. And then if you make, again, the same thing, projective measurement means that you will take these projections here and you will subtract one from another, P0, P1. Okay. So if you do this with U3, what you get is where is it? I don't show here. I don't show here. But yeah, I think on last seminar I did this calculation. I will not do again. But what you get when you do P0 3 minus P1 3, this is exactly what we had before. This is cosine theta, which was just the z component. Okay. But what I wanted you guys to do is this for the x and y components. So there is also these rotation matrices U1 and U2. Okay. And when you rotate this U1 and U2, when you rotate the vectors over this U1 and U2, and subtract P0 minus P1, what you get is this X component and Y components. Okay. So again, these are rotation of 45 degrees, but now, as you see, the entries are complexes. So the entries are complexes because it's not rotation over the over the z axis, but it's rotation over the x and y axis. And what you get exactly is these components x and y at the same way. Okay, so these unitary matrices are also interesting because they represent rotations, and because when you make this sandwich, you also get these x and y components. Okay. All right. So I think this was home assignment I gave last seminar, but it was not clear. It was not on the board. So here I put clearly. Again, I think Valeria discussed with you guys, and I confirmed this, that the home assignments, you just don't need to deliver on the next seminar, but you can deliver until the end of the course, until 13 of June. Okay? Feel free. I think like this, more people will have chance to do these calculations. So the point here, again, is the same thing. Calculate these elements. Okay, so you will do P01, for example. I will just write here quickly. P01 will be modulus squared of probability of this psi1 be on the 0 state. And P0, P1, P11. This will be the probability of finding this rotated state on the 1. Okay. When you subtract these two guys, you get x. When you subtract, in the case 2, using the rotation U2, what you get is this y. Okay. So I would like home assignment to see these demonstrations. So it's just like this. Just take these guys and as I did here with P3, okay? Take like this. So P0 is contraction with 0, P1 contraction with 1. Take modulus squared and subtract 1 minus the other. Okay? And do this. Show this. Okay, this exercise I think I can do myself now. So exercise. The fidelity F of two quantum states psi1 and psi2 is defined as F equals, by the way, there's an extra bar here, should not be. We'll remove this typo later. So what we have is that F is this inner product, psi1, psi2. Let's say psi1 and psi2 are arbitrary quantum states, right? So it is, the fidelity is a measure of the distance between the two quantum states. If we have 0, it's low fidelity. If we have 1, it's maximum fidelity, right? So fidelity equals 1 when psi coincides, psi1 coincides with psi2, and F equals 0 when psi1 and psi2 are orthogonal. They are orthogonal means they are crossing each other on a 90 degrees angle, right? So the exercise here is show that F equals cosine squared of alpha over 2, with alpha the angle between the Bloch vectors corresponding to the quantum states psi and psi2. I think I can do this. So the idea is that we can represent the vector psi1, right, as cosine of theta over 2. Will this be the longer way to do? One way to do this would be like this. Cosine of theta over 2 plus e to I phi 1 sine of theta over 2 times 1. And same thing for psi 2, right? So psi 2 equals, by the way, here we need 1, theta 1, theta 1. This will be cosine theta 2 over 2, 0 plus e to I phi 2 sine theta 2 over 2, 1. So when we make the inner product between these two vectors, what we have to do here is to do psi 2 inner product with psi 1. So what we will have just 0 with 0. This will be cosine of theta 1 over 2 cosine of theta 2 over 2 plus e to I phi 1 minus phi 2 sine of theta 1 over 2 sine of theta 2 over 2. And when you take modulus squared of these two guys, so if you take here modulus squared, this will be modulus squared. We should take the modulus squared of this thing, but this will take a lot of time, and maybe I don't have space in this screen to do all this calculation. But that's the idea. At least this is the way to calculate this stuff. So in the end, what you will have here is this the expression for this angle. You cannot see notes on the board. Really? Can you other people see the calculations I'm doing on the board? No. Oh my God. Thank you for telling me. Thank you for telling me. Wow. I'm doing a lot of calculations and nobody is seeing this. Let me try to solve because I think I needed to share the whole screen. This is, I'm sorry, guys. Thank you for telling me. I was sharing just the tab, not the screen. It's a big mistake. I think you guys can see now. Yes. Oh my God. I'm sorry. I already did a lot of calculation. Thank you for telling me. Thank you for telling me. Yeah. So how could be a simpler way to calculate this stuff? So because maybe I don't have space. Yeah. But the result is this one. When you take spherical coordinates, you should express this in terms of theta 1, phi 1, sine of theta 1. Okay, this is for vector psi 1. And then there is the vector for 2. So this is cosine of theta 2, phi 2, and sine of theta 2. When you do like this, you can take the inner product between these two vectors, psi 1 and psi 2. So you will get something like this. And this is cosine squared of alpha over 2, the angle between these two vectors. So the point is that if you have a vector psi 1 and another vector psi 2, this is the angle between them, alpha, right? So this fidelity gives the cosine squared of this angle alpha. And takes a lot of algebra, but the point is that this can be interpreted as the inner product, right? So if you have two vectors, v1 times v2, this will be modulus of v1 times modulus of v2 cosine of this angle between them, cosine alpha, right? But because in our case both vectors has modulus 1, so this modulus is 1, this modulus is 1, and we just have this cosine of alpha here. But remember that in our result is cosine of alpha over 2, okay? So this would be a way to calculate this stuff. Would be going over the inner product of these two vectors, as I did here, right? So as I did this this inner product here. This is how you get this relation, okay? Okay, circuit model of quantum computation. As was shown in the previous lectures, a classical computer may be described by most conveniently as finite register of n bits, right? So should I make a pause here, or it's in 12:30? Let's do like this, right? 12:30 we make a pause, and at 1 we go back, right? Okay. So in the classical computer, we saw that we have most convenient form of writing numbers. We can use these bits of 0 and 1s, right? These states of 0 and 1s. And this is how Alan Turing conceived all these results and so on, how he conceived how to make operations and so on. To do that, we needed these gates, logical gates, right? Not, exclusive, not, or, and, exclusive, and, blah, 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 and so on, right? So elementary operations such as not or and may be performed on single bits or pair of bits, and these operations may be combined in in order way to produce any given complex logic function. So the idea is that we will represent functions using these gates, right? So the circuit model can be transferred to quantum computation. The quantum computer may be thought of a finite collection of n qubits and a quantum register of size n. So you will store your information in this register of size n, so n qubits, right? And this quantum computer will be the device who will take these bits, perform some operation, and have some outcome. Okay? So let's go. This is where notation might get heavy. So while the state of n-bit classical computer is described by a binary notation, so integer I belonging to this this was wrong here, 2n minus 1, okay? 2 to power n minus 1. This is a typo. There's a typo here. I didn't have much time to check the typos in the presentation, sorry. But yeah, in this case, it's clear. So the idea is that if you want a number from 0 to the power 2n minus 1, let's say you want to represent some number from 0 to 32, 0 to 31, right? So from 0 to 31, you need 2 to power 5. 2 to power 5, you will have 32 numbers. And then if you start counting from 0 to 2n minus 1, so n is 5 in this case, right? You can represent this number using this notation here. So I equals in minus 1 times 2n minus 1. In minus 2 times 2n minus 2. Da, 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 until I1 to power times power 2 plus I0 to 2 to power 0, right? So these digits are so-called binary digits, and they can represent numbers in these integers in this range, okay, from 0 to 2 to power n minus 1. That's some beautiful, beautiful results. So in the quantum computer, the idea is to have your state psi decomposed into arbitrary number of states. So for example, if you have from 0 to 2n minus 1, right? And these coefficients should have some amplitude. And this would be some linear combination of these quantum states, right? So I prepared 2n minus 2 to power n qubits, put them in parallel, so to say, and then you have your quantum state, your general quantum state for your system. Okay, so we call this n qubit quantum state. In this case, we want to do n qubit quantum computing, right? And the point, this is where it will be a little bit of mathematics, so I hope you guys also can follow what I'm doing here. So here we'll do this concept of the direct product. Okay, so this is an X with a circle around. Okay, so outer product. So the outer product between these states generates a precise quantum state. Okay, so instead of having now these summations over all these possible quantum states, it will be clear soon because I will give example with a definite number of states. Okay, so in this case, it will be a summation from all these qubits of the direct of the outer product between these individual quantum states. So this part here refers to the general state, quantum state of all the qubits, and each of these states is referred to the individual states of each qubit. Okay, and again, these amplitudes, they follow this normalization condition, right? So this is summation of these coefficients, Ci here. This is modulus squared of Ci equal to 1, summation, okay? Let's go for example, because I think with a simple example, it will be better. What is the example? Yeah, this. So first to say that technically the state of n qubit quantum computer is a wave function residing in 2 to power n dimensional Hilbert space. I just meant that before, for 1 qubit, we had Hilbert space, right? Two-dimensional Hilbert space, because it was a vector with two components, 0 and 1, right? It was two-state quantum system. Now, for the n qubit quantum state, the Hilbert space will be 2 to power n. Okay, so the vectors here, they are now in the 2 to power n dimensions. Okay, so it's a tensor product or outer product of this n two-dimensional Hilbert spaces, one for each qubit. So remember that individually, each qubit in our case here has two entries, 0 or 1. And then when we make a combination of many qubits, n qubits, you have a n two-dimensional Hilbert spaces, as it should be, right? Take into account the normalization condition and the fact that the state of any quantum system is only defined up to a global phase of no physical significance. The state of the quantum computers is determined by 2 to power n minus 1 independent real parameters. Let's see what this means with the example, right? So as an example, let's consider the case with n equal to 2 qubits. So it will be, again, each qubit has state 0 or 1, and we'll put in parallel, let's say like this, in parallel, 2 qubits. So in classical computer, this would be just 2 bits next to each other, one with 0 or 1, one with 0 or 1, right? But now we have 2 qubits. Will be this quantum state for this qubit, quantum state for another qubit, and this combined system, it has a larger quantum state. Okay, someone wants to go in. Yeah. Okay. So now we have this generic state written like this. So now this, you see here that we have the states 0, 1, 2, 3. What this basis means now? This means that, again, as you saw, we have this range from 0 to 2 to power n minus 1. So this means that it will go from 0 to 2 to power 2 minus 1, which is just limits from 0 to 3. What this means? What this means is that now we will have this outer product or tensor product between each individual state of the qubit. So this, what we call here 0, is actually now the combination of the 0 state in the qubit 1, in the first qubit, and the 0 state in the second qubit. This one here that we call, this will be a combination from 0 state in the first qubit, 1 state in the 0 qubit, and so on and so forth. So the 2 will be 1 in the first qubit, 0 in the second qubit, and 3 will be 1 in the first qubit, 1 in the 0 qubit. So now you see that previously each quantum system isolated, it had this simpler vector. It was just 2 by 2 vector. But now when you put both of these quantum systems in contact, you just increase the dimension of the system. You will see that this will increase the dimension of the system. But for sure here you have now 4 states to describe this quantum state. You have 0, 1, 2, 3. This will be our new operational base. So for simplicity, we are going to write like this: 0, 0, 0, 1, 1, 0, 1, 1. So this will be our convenient base, or our operational base, our computational base. And these coefficients will be written like this: C00, C01, C10, C11. Okay? This will be our coefficient. So we conveniently wrote like this final state here, right? I0, I1. So I0 can be 0 or 1. I1 can be 0 or 1. This will be the direct, the outer product or the tensor product between I0 in the first space and I1 in the second space. I will show how to do this calculation. So I better do now. Yeah, I better do now. So how to do this product like this? So this product can be done. For example, let's say I want to do the 0, 0 direct outer product or tensor product. So this will be this product here. 0 is 1, 0. Outer product with 1, 0. Right? So what we will do? We will have now some 4-dimensional vector. And it will be like this. 1 times the first vector. I will just put here like this. 1 times first vector. And the second entry, so 1 times this vector. And 0, second entry, 0 times this vector. Will be 0 times this vector. Okay? So the final result will be something like this. 1, 0, and 0, 0. So you see now that this product from 2-dimensional vectors produces 4-dimensional vector. Okay, it increased the dimension of the system. Okay, and so on and so forth for all the vectors. So for example, you can check yourself, but let's do, for example, 1, 0. Oh, not 1, 0. 1 tensor product with 0. So this will be 0, 1. Let me make a little bit more. 0, 1 tensor product with 1, 0. So what we have here, we have something which is bigger, and we will have 0 times the second vector. This is pure notation. You guys can remember, right? So it will be like this. 0 times this vector plus 1 times this vector. So it will be just 0 times this vector, 1 times this vector. So this will give 0, 0, 1, 0. This is this product here. Everything clear? How to make a outer product? If you want, I can make another example. Should I make another example? 1 times 1, maybe. 1 times 1, for example. So it will be 0, 1. Direct tensor product, 0, 1. This will be a larger vector, and it will be 0 times second vector. So 0 times 0, 1 times 1 times 0, 1. This will give, in the end, 0, 0, 0, 1. Okay. So you guys can see that this new base is exactly, I will delete. Okay. So this new base, what it gives, this new base here, 0, 1, 2, 3. It's exactly made by these direct products, and this will be like the canonical base, this will be like 1, 0, 0, 0. This will be this new 0 vector. The 1 vector will be 0, 1, 0, 0. The 2 vector will be 0, 0, 1, 0. And the 3 vector will be 0, 0, 0, 1. Okay. I think I will show this ahead. So, but just to show that how this notation makes life much simpler now. This notation makes our life much simpler because these coefficients, they just have the entry for each state they represent, right? So, for example, if we are on 0, 0, this will just be 0, 0, and this will be C 0, 0, right, as before. The general case is shown here below, okay? And the superposition principle is clearly visible in our previous expression. So while n classical bits can store only a single integer I, the n-qubit quantum register can be prepared in the corresponding state I of the computational basis, but also in a superposition. Yeah. So you see that we immediately enhanced our range of parameters, right? So previously in the classical bits we have either 0 or 1, but now because of superposition, we can have this linear combinations of these vectors, and we will have, as we did before, as we did here, right? So we will have all these linear combinations like this, and because of this linearity, we are going to have superposition, right? Superposition principle. It is important to note that the number of states of the computational basis in this superposition can be as large as 2 to power n, which grows exponentially with the number of qubits. Yeah, 2 to power n, this is immediately exponential. So this superposition principle opens up new possibilities for computation, right? When we perform a computation on a classical computer, different inputs require separate runs. So what I mean by this, different inputs. So if I give different initial states and want to have different results, I need to run this experiment every time I want to have different results. So this is a bit limiting for classical computer. But in quantum computer, it can perform a computation for exponentially many inputs on a single run. So if you have now exponential number of states, and you can collapse this wave function, you can make one experiment and collapse this whole wave function at the same time. I know that the wave function has many dimensions. That's true. You will have to measure each of these components of the wave function. But if you can do this at the same time, it means you will have a very fast result for your experiment, even when you have very long, very large apparatus, right? So this huge parallelism is the base of the power of quantum computation. Okay. In order to perform a quantum computation, one should be able to, number one, prepare the quantum computer in a well-defined initial state. So I can be able to restart this computer all the time in the state psi I, let's say initial, right? Let's call this the fiducial state of the computer, the state that you can trust, right? So for instance, the ground state of all the qubits, so 0, 0, 0, 0 for all the qubits. I have to be able, number two, I have to be able to manipulate the wave function, this generalized wave function of the quantum computer. So I have to be able to drive any given unitary transformation U, leading to some final state psi f in terms of U times psi I. So I will be able to do some unitary transformation. I will be able to do some kind of rotation in this higher dimensional sphere, the Bloch sphere, right? I'll be able to do some arbitrary rotation there, make the measurement, and get my result. Okay. At the end of the algorithm, perform a standard measurement in the computational basis and measure polarization sigma z of each qubit. For example, right? For example, polarization For example, the spin component of the spin. There are many, right? As you know, there are many implementations for this. Okay, guys, let's make a break here. I will eat something. In half an hour, we'll go back, okay? Let's go back at 1 p.m. All right? So see you soon. See you soon. All right, let's wait 5 minutes so everybody goes back. All right. Let me see. So let's continue with these single bit gates. Okay. So a single qubit gate, right? So what we have seen before was this general register with many qubits, right? Now we are going to talk about gates with single bit, and then we try to go for the general case of gates and many qubits together. Okay. So for single qubit gates, you remember that in single bit gates was this identity bit. You just go in with 0 or 1, and then it returned exactly with the same value. So if it was 0, it was 0. If it was 1, it was 1. Return 1. So now there are also these gates, but we are go straight forward for these more complicated forms. Okay, so these are the Hadamard gate and the phase shift gate. Okay, maybe we discuss others also, but I will pretty much just give examples of what are important gates now. In the next seminar, we can talk more about gates. But it's just to give a feeling of how this stuff will operate. Okay, so the operations on a qubit must preserve the normalization condition, right? And therefore they are described by 2 by 2 unitary matrices. So 2 by 2 unitary matrices, as we saw, uh, the conjugate Hermitian conjugate times the unitary matrix gives identity matrix. So when you make sandwich which with both operators, you don't change your state vector, you don't change expected values, and so on, right? So we can operate them freely. Okay, so we are going to introduce these Hadamard and phase shift gates and show that they are sufficient to perform any unitary operation on a single qubit. Okay, so let's go for Hadamard gate. So this Hadamard gate is defined like this. Remember that the other case we saw was a bit different. So what we had was the rotation. With rotation, what we had was 1 over square root of 2 times 1 minus 1, 1, 1, right? Because this is cosine, sine, cosine, minus cosine, minus sine, cosine. So this was exactly like something like remembered like a rotation. But the Hadamard gate is different. So the minus sign appears here in this lower part. Okay. So this gate turns the computational basis 0 and 1 into the new basis plus minus. And the states are a superposition of the states of the computational basis. So if you apply Hadamard gate on 0, what you get is 1 over square root of 2, 0 plus 1, right? And we define this as the vector plus. In the second case, what we have is h times 1. This will be 1 over square root of 2, 1 times minus 1. I think here it's worth to make this matrix multiplication because it's very simple, right? So in one case, what we have is h times 0. So it's basically 1 over square root of 2. This 1, 1, this operator, right? 1, 1 minus 1 times 0 vector. This is 1, 0. So what we will have just 1 over square root of 2 times 1, 0. Oh, wait, sorry, 1. And then 1, 1 here. Okay. So what is this? This is exactly, if you divide this in the old base, this will be 1 over square root of 2 times these two vectors. One, let's put with this because it's more beautiful. So it will be 1, 0 plus 0, 1. Okay. And in our definitions, this is the 0 vector and this is the 1 vector. So this is exactly what we have there, the result. 0 plus 1. Right? And vice versa with this guy also, with the h times 1. It will be the same thing. 1 over square root of 2. The operator, apply, times 0, 1. So be equal to 1 over square root of 2, 1 minus 1. And from now, in same shape, we will have 1 over square root of 2, right? What we have there, 0 minus 1, right? So here there is also another note. Since h squared equal identity, the inverse transformation h to minus 1 equals h. Note that h is Hermitian, which means we can take the complex conjugate and transpose the matrix. It will be the same matrix. And indeed, it is evident from the matrix representation that if you take the conjugate and transpose, it will be the same matrix, right? So h squared equal 1. I think this is very clear, and yeah, everything clear. I think it's clear. If I multiply, you can check this yourself, but if I multiply h squared, this minus here will kill the off diagonal terms, so it will be 0 here. Oh no, sorry. This minus here will maintain everybody with the same size. So it'll be 1, 1 minus 1. How to do in a quick way? I just want to show that h squared, this will be 1/2 of 1, 1, 1 minus 1 times. You can check this yourselves, but it will be exactly this 1/2 of 2. Here will be 0. So my point is that this minus sign kills the off diagonal terms. Then 0, 2. And then because of 1/2, this will be 1, 0, 0, 1. Right? So there you go. So we demonstrated this property, h squared equal to the identity matrix. And because this is real numbers, it's very clear, and the matrix is symmetric, that if you take the complex conjugate and transpose, it will be the same matrix, right? So everything is clear. There is also the phase shift gate, right? So let's define this phase shift gate with this matrix. So this is diagonal matrix, but in the second part here, there is a phase shift. So now this matrix is complex, but because it's symmetric, it's still Hermitian, right? If you take the complex conjugate and transpose, right, it should be the same. Yeah. So this gate turns 0 into 0 and 1 into this, right? It's clear, right? Because 0, if you apply R z over 0, this will be 1 0 0 e to I delta 1 0. This selects only the upper part, so it will be, the matrix will be just 1 0, which is just 0, right? But if you do R0 on 1, then it will select the lower part. So what we will have will be that result. So this will be 0 1. This will be exactly 0 and e to I delta. This will be to e to I delta times 1, right? So this gate turns this vector into this vector into this. Since global phases have no physical meaning, the states of the computational basis 0 and 1 are unchanged. So it means that if I do the inner product of this transformed vector with itself, this phase will become plus minus I delta in the sandwich, and then they will kill each other. You will have the same inner product, right? It will not change. But the action of the phase shift gate on a generic single qubit state psi gives this. So what you see here is that this product of this matrix will shift this lower part here by delta. So in the Bloch sphere, if we had theta as the polar angle and phi as the azimuthal angle, so the effect of delta will be, of course, we are choosing deliberately RZ, right? So this means this is rotation along the z-axis, rotation around the z-axis. Okay, so it means that phi will be shifted by delta, right? It is easy to recognize that this equation, this gate generates a counterclockwise rotation through the angle delta about the z-axis of the Bloch sphere. Okay. It is important to realize that any unitary operation on a single qubit can be constructed using only Hadamard and phase shift gates. Actually, a unitary transformation moves the qubit state from one point of the Bloch sphere to another point, and this can be obtained only using these two quantum gates. In particular, the genetic state above, which can be reached starting from 0, as follows. So that's, now we are going to try to generalize everything here, guys. So with combinations of Hadamard gate, rotation, Hadamard, rotations, we are going to be able to produce any arbitrary state that we want. That's the main result that we are going to do here. Okay, so again, remember that Hadamard, I'll put here on top. So Hadamard is 1 over square root of 2, 1, 1, 1 minus 1, right? And rotation. Note that here we have rotation over theta, and here is rotation over phi plus pi over 2, right? But just remember that rotation z of delta was, was something like this: 1, 0, 0, e to I delta, right? So there you go. What we have to do is to start with this state 0. So it means we'll start with, let's do here on the corner. Probably. Maybe I can, let me try to do something. I made it worse. Yeah, for now, I can leave it like this. Yeah. So again, we know that Hadamard acting on 0, this will be 1 over square root of 2, 0 plus 1. Right? We saw this before. And Hadamard acting on 1 with a minus sign. Right? So we need now to act the rotation of theta on this resulting vector. So the idea will be to do rotation of theta over 1 over square root of 2. So maybe I can already go closer to the result. Will be 1 over square root of 2 times rotation z of theta times 0 plus rotation z of theta on 1. Right? So basically, I'm applying Rz of theta on this resulting vector here. Okay. And we saw before that this phase shift brings 0 into 0 and 1 into e to I delta times 1. So what we are going to have here, what we will have is, I'm sorry if it's a little bit messy, but it's too much calculations to do in LaTeX in this presentation. So sometimes I just need to come here and do the demonstration. I mean, if it's too much trouble, we can just trust the result here. But I would like to show what is the idea behind, So the idea behind it is this rotation will act on this vector, and this will be 1 over square root of 2 times 0 plus e to I theta times 1. So as we saw, rotation over z doesn't affect 0 and affects 1 with a phase factor, right? Like this. Now next point. Oh, sorry. Let's see. Let me fix this. Yep. So the idea now is act with Hadamard again on these vectors. So h 1 over square root of 2, h acting on 0 plus e to I theta, Hadamard acting on 1. Okay. So this will be 1 over square root of 2, h over 0. Again, we can even divide this, so it will be 1 over square root of 2 times 0 plus 1 plus e to I theta divided by square root of 2. which multiplies 1 over square root of 2 times 0 minus 1. Okay, this is the second last stage. So the last part we need, let me do this. Where do I do this? Maybe above here to finish. We need to apply the rotation z of phi plus pi over 2 on this result here. Okay, so let's call this result here second last, right? SL, second last. So this thing applied on the state second last, this will be 1/2 of so rotations, we know that it keeps 0 as 0, so this will just be 0 like this, plus e to I phi plus pi over 2 times 1, right? Plus e to I theta over 2 times 0 minus e to I phi plus pi over 2 times 1. So when you combine these two terms here and take away this e to I theta over 2, you see that you get exactly this result here. So if you check, you can check that you will get e to I theta over 2 times cosine y cosine, because the sine part will cancel when you sum this 0 with this 0. Okay, yeah, you will get exactly this theta over 2 times 0. Plus this I to pi over 2, this will just bring, we know that e to I pi over 2, this is exactly I, right? So this is a factor of I multiplying this term and this last term. So when you multiply by I and subtract both numbers, you just get the imaginary part. So what you get here is exactly e to I phi times sine of theta over 2 of theta, sorry. No, fine theta over 2, yes. Times 1. Okay. So there you go. This is exactly this result here. And the point is that unless you can cancel this phase out. Let's say we make that trick just to take the modulus and so on. You get exactly a connection between the ground state 0 and any arbitrary state, just with this Hadamard gate and phase shift gates. Okay, I will delete now. So this is more or less the calculation you need to do to get this stuff. So now let's go for the, let me check here. Yeah. Now we are going to talk about something that is very critical to all of this, is entanglement. Okay, quantum entanglement. That's the the word now in this point. Okay, so these gates, they introduce something that complicates a lot the system, but complication is good in our case. Okay, so you saw that before we were in the stage 0, right? So previously we had the stage 0, and just applying these gates, okay, we got to any state that we want. So this means that um, these gates introduce complication to your system. These gates entangle the states, these gates, right? So entanglement, which is the most intriguing characteristic of quantum mechanics, appear already with 2 qubits. Actually, a generic 2-qubit state can be written in the computational basis as, so again, computational basis is this basis where you just take the outer product of 0, 0, 0, 0, right? 0, 0, 0, 1, something like this, right? And so on. So you get this new base, and with this new base and with these coefficients, this is the point where you have entanglement, quantum entanglement, okay? Again, these coefficients, because of normalization, they should add up. When you take modulus squared, they should add up to 1, these coefficients. We are doing here the 2 by 2 case, or the 2 qubit case, right? The fact that the state is only defined up to an overall phase factor, so remains 6 degrees of freedom. Do you guys understand what I mean here by 6 degrees of freedom? Because each of these coefficients here, they are complex numbers, right? So they have the imaginary part and the real part. So each of them has 2 degrees of freedom. So it means in principle we should have 8 degrees of freedom. But because you need normalization, so you reduce freedom. Because you need this normalization, degrees of freedom go down to 1. And because the general phase of this wave function, as we saw, right, we can make always a transformation and change this guy to some phase here. So because we can always change this, and this will not change the sandwich with other wave functions. So for example, if I do this, right, if I do this in a product here, if I do this inner product, it will not change the result. So the point is that this is also another degree of freedom that goes away, which means that instead of 8, we just have 6 degrees of freedom. Okay? But what about this entanglement? Quantum entanglement is the phenomenon that happens when a group of particles is prepared or created, interacting, or sharing spatial proximity in such a way that the quantum state of each particle of or the group cannot be described independently of the state of the others, including when the particles are separated by a large distance. So they are entangled. They are like connected to each other. You know, entanglement. I don't know exactly the word in Russian, but the concept is this. The concept of entanglement is like when there is a, for example, love relation between two persons. You know, you say that their souls are entangled. You know, so the idea is that you have deep connections with this person. And the topic of quantum entanglement is at the heart of the disparity between classical and quantum physics. Entanglement is a primary feature of quantum mechanics not present in classical mechanics. Okay, so indeed, I state psi of a bipartite quantum system, so as quantum systems that are composed of 2 subsystems, is said to be separable when it is possible to write psi equals psi1 outer product psi2 with psi1 and psi2 wave functions for the 2 subsystems. Okay, Therefore, a separable 2-qubit state has only 4 degrees of freedom, since in principle we can take for each qubit the 2 parameters of its block sphere, right? So the angles in the block sphere, you remember there's 2 angles. So in principle, these 2 separate states, they produce 4 degrees of freedom, right? And the situation becomes more complex on increasing the number of qubits. One may say that the complexity of entanglement grows exponentially with the number of qubits, while a separable state of any n qubits depends only on 2n real parameters. The most general entangled state has 2 times 2 to power n minus 1 degrees of freedom. Okay. I mean, yeah, the most general for qubits. Okay, someone wants to go in. I'm a little bit bugged. Person left. Oh, this was so quick. I didn't even have time to accept the person to go in. I went back. 2 to power n minus 1 times 2 degrees of freedom. Okay. So we'll see here. It is clear that the single qubit gates are unable to generate entanglement in an n qubit system. Indeed, if we start from a separable state, if we start again from a state psi that is made of the outer product of these states in subsystems, right? We can move at will any qubit on its block sphere, obtaining this new state. So let's say we have a quantum state composed of many subsystems. We can rotate, apply these Hadamard gates, phase gates, phase shift gates. We can always change them individually. And the point is that we are able to do this with the arbitrarily large, more complex n qubit system, right? So I say here any state of type psi I can be transformed by gates acting on the qubit I in whatever superposition of states 0 and 1, but the n qubit state is still separable. So if I start from the subsystems and change them, so in principle, the resulting state is still separable. They are isolated from each other, and I'm changing them isolated from each other. So I have this subsystem here. I apply some gate in this subsystem. I will change this subsystem, and this general state of the system will be a more complicated one. But as I just acted on this subsystem, the whole wave function is still separable. But in general, it's not like this. So to prepare an entangled state, one needs to interqubit interactions. So we need to make interactions that kind of mix these two qubits together. Okay, that is a 2-qubit gate. So we now are going for a more elevated level of gate, of quantum gate, that mixes this. So it introduces interactions between these two gates. I will give some examples. Okay. So, but let's talk about prototypes. Prototypical 2-qubit gate that is able to generate entanglement is the controlled NOT gate. Okay, this gate acts on the states of the computational basis, right? So this is our computational basis. Again, repeating, right? And it acts as the classical exclusive OR gate. This is called the controlled NOT gate. Okay, remember this guy. It's very important. Controlled NOT gate. Okay, so it acts like this. Controlled NOT acting on this pair, right, of qubits. It will reproduce the first one and make a direct sum or addition modulo 2. You guys remember, right? This addition modulo 2. It means that we sum like 1, 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2. This is already 2, so we go back to 0, right? So this is the addition modulo 2. And x and y in this case are zeros or ones, right? So they can be this state or this state, right? The first qubit in the C0 gate acts as a control and the second one as a target. So we will keep the first guy not changed, and the second one will be a mix of the result of the C0 gate acting on both of them simultaneously. Okay, so the gate flips the state on the target qubit, on the lower one, if the control qubit is the state 1, and it does nothing if the control qubit is in the state 0. So as discussed before, the basis vectors can be discussed as column vectors, right? So as I mentioned before, so 0, the one we called 0 was this, the one we called 1 was this, the one we called 2 was this, but it's actually made of the outer product of the states 0 and 1, right? So this was actually made of this outer product. I'm repeating a lot because maybe it's too many new concepts, too many new definitions, so I'm being very repetitive on purpose, okay? So you guys understand. Make sure you guys understand this stuff. So this product, right, as you remember, this was this product, right? This was this product, right? Resulted in this. We did these multiplications, right? Yeah. Yeah. So as we saw before, right? So the target qubit, the gate flips the state of the target qubit if the control qubit is 1. If it's 0, it does nothing, right? Let me see. Did I show this stuff where? Yeah, here. It's here. That's the C0 gate. So basically, if it will flip the target qubit. So the target qubit, as we saw, is the second one, right? Second one. This is the controlled node. So if the control qubit, this first one, if the control qubit is 1, it flips the second one. If the control qubit is 0, it will do nothing, right? Clear, понятно? So you can see the C0 is this, it has this representation. So the control will be kept the same. It will be just ones in the diagonal, right? In the control qubit. And in the target qubit, it will flip it. So if this guy is 1, it will be 0. If this is 0, it will be 1. So in these last two states here, it will be the reversed I, like this. So the components of C0 ij is the matrix given by these elements here, right? So I and j, again, this is made by I goes from 0 to 3, right? So it's 4 by 4 matrix, right? I goes from 0 to 3, and these combinations all go from 0 2, 1, right? All these combinations here. So you get this matrix. Okay, you can make all these projections. For example, if you want to get the element, if you want to get this element here, this is the element I equal to 1, j equal to 2, right? So it means that this is row 1, column 2. So then you have to make this sandwich here to check what is this element. So you need to put vector 1, C naught, then you put 2, okay, and this will give these elements, the matrix elements of this operator, okay. Yeah, I show here an example, right? C naught 2, 3. This is the sandwich between states 2 and 3 on this gate, on this operator, right? Which in the other notation is 1, 0, and this is 1, 1, right? And we obtain this is 1. So when you go to this matrix here, see that was this guy here or this guy here, right? Of course, the C naught gate, in contrast to the classical XOR gate, can also be applied to any superposition of the computational basis states. Yeah, of course, you can always build some arbitrary state psi, right? And apply C naught to this arbitrary state psi. So this will be, you know, individually how it acts on each of these members. So let's say you have, if you have some state psi defined as alpha 0 plus beta 1 plus gamma 2 plus delta 3. So you know how C naught acts on each of these guys. You can just use the superposition principle and act them separately, right? Note that, again, C naught is self-inverse. So if you make C naught squared, you get identity matrix, right? I think it's easy to see this because this matrix here, this is already diagonal. So if you multiply, there will be just identities. This is block diagonal matrix, which means that only these blocks play into role. These guys are 0 and these guys are 0, right? 0, 0. So you just need to analyze this matrix separately. And it's clear that this matrix is self-diagonal. If you multiply this matrix by itself, you will just get the same thing, right? 1, 0. This will be 1, 0, 0, 1, right? So it's clear that this term squared will also be diagonal, right? Yeah. And it's clear now, the key point here, the C naught gate can generate entangled states. That's the main point, entangled state. For example, C naught acting on a state like this, alpha 0 plus beta 1, direct product with 0, will be something like this, right? Alpha 0, 0 plus beta 1, 1. So this is non-separable. There is no way that you will build two individual states that will result on this state here. So previously what you had was a separable state. So previously you had this state, right? 0, 0 plus alpha 0, 0 plus beta 1, 0. Means that in this state here you can produce these guys with tensor product. What I mean by tensor product is you just take this individual state, alpha 0 plus beta 1. This is one separate subspace. This belongs to one separate subspace, right? This is tensor product with this guy. This is the state in the second subspace, or in the second qubit. So in the first qubit, I had this state, right? And in the second qubit, I had this state. So it means that your total state, so the state of all your larger quantum group, quantum system, it was not entangled. It could be separated into two subspaces. But when you acted with this C0 gate on this state, you got an entangled state. This state here, it cannot be produced by an operation like this. It cannot be produced doing a direct product of two subspaces. Okay, and this is very useful for us for calculations. Is that clear, guys? Any questions? Maybe it's too confusing. What is the feeling so far? Okay, no questions. Then we can move on. Maybe I already lost you guys. In some point, again, you can interrupt me at any point if it's not clear for you. You can interrupt me. So here, maybe, so we have already one home assignment for the review part, right? But the home assignment today would be to show this. So the most general separable state of two qubits can be written up to an overall phase as this product here, right? So it's a general qubit on this side, outer product with another qubit on this side. So this is the most general separable. The key word here is separable, right? Because we can obtain this state doing this outer product, right? What conditions should the real coefficients B0, B1, phi0, and phi1 satisfy in order that C0 on psi be entangled? So what are the conditions for these phases in this amplitude here, in such a way that always when I apply C0 on psi, I get non-separable, or I get entangled state? I cannot reproduce this by doing the direct product, the outer product of these two separate vectors. So this is second home assignment, but maybe it's a little bit more complicated than the other one. So you guys can maybe solve first the first one, and if you have more time, you can go for the second one. Okay. It is also possible to define generalized controlled NOT gates depending on whether the control qubit is the first or the second qubit, and whether the gate acts trivially when the control qubit is set to 0 or 1, right? Yeah, trivially when we set the control qubit 0 or 1. We say that the gate acts trivially if its action reduces to the identity. What I mean here? What I mean here is that there are other ways to represent the C0 gate. So this was the one we saw before. This is a representation of C0 gate as we saw before. So again, it's diagonal in this first block, right? It's identity in the first block. But in the second block, it's off diagonal, like this, right? But there are other ways to represent this depending on which one is your control, which one is your target qubit, and what is the action if you're going to flip this if this is 0, or you're going to flip that if this is 1, something like this. Okay. So here is if you just change who is target and who is control, you will get exactly the opposite of this, right? So identity here on the lower part and off diagonal on the upper part. And these other two, they happen when you define that instead of 0, you flip. When it's 1, you flip. You know? Let me review here because I'm not sure. So the control qubit, it flips the target qubit if the control is 1 and does nothing if it's 0. So in these new cases, it will do nothing if it's 1 and flip if it's 0. So in this case now, you get this very strange formulations where it's not block diagonal anymore, and you have ones here in this part and in this part. Or here, if you change who is control and who is target, you get here and here. So very strange formation. Okay. So the first matrix A is the standard C0 gate. B flips the second qubit if the first is set to 0. C flips the first qubit if the second is 1. And D flips the first qubit if the second is 0. So it's all the possible combinations for this C0 gate. And the representations for these gates are done like this. So this is your, for example, right? For example, this can be your control qubit. And this can be your target qubit. Okay. And this is the symbol for the C0, controlled node. Okay. So if you do the first one we showed, this will be the symbol. If you change the definitions to as the way we did before, right? So these matrices that we saw before, A, B, C, D. So each of these matrices, each of these are formulations of the C0 gate, and all of them has these different symbols here. So this, and these two firsts, we flip who we define who is control and who is target in a way, and in these two ones, we define who is control and who is target in another way. And in these two ones, it flips if it's 0 or if it's 1, and these other two ones, same thing. It flips if this is 0, if this is 1, right? From these matrices here and from the definitions, you can guess who is who, okay? So, but this is respectively. This is matrix A, B, C, D. In circuit language, this is how it's represented. So guys, from here you can already see that we are getting closer and closer to those little diagrams of computations, right? That we did in the classical computers. So our objective will be at some point tomorrow in the next seminar, in the next week, to do also some algorithm using these gates to some uh, to some 2 plus 3, for example. I think we did this in the last case. We did 2 plus 3, right? Yeah. So let me check here. We go until this 2:20, right? We have 23 minutes more. Maybe I release you a little bit early. Let's see if I can finish this material up to the end. So as usual, in these graphical representations, each line corresponds to a qubit, and any sequence of logic gates must be read from the left input to the right output, right? As usual. We did this before in the classical representations also, right? Okay. From bottom to top, qubits run from the least significant, I0, according to binary notation shown before, to the most significant, IN minus 1. So this means that what we have here is that here enters I0, and here will enter I1 states, right? So this is your separate subsystem that will go in here. So this gate acts like this. This part acts on the most significant part of your, the label, highest label, and this happens on the lowest label, okay, I0. So previously we were representing numbers like this, right? I0, I1, I2, etc., right? So this means that now that in this n qubit state, it will act like this. The from bottom to up will be these labels. This is just the definitions of our notations, right? Here, a qubit is said to be more significant than another if its flip gives a larger variation in the integer number coded by the state of the n qubits, right? Yeah, what it means is that you can be in a quantum state that if you flip from plus to minus in this particular qubit, it will produce more noise into your result. It will be producing more significant deviation in your results. Okay, let's exemplify that. Maybe this thing is in the wrong. Let's exemplify that. What was the point of putting this here? I had an example. I had prepared an example to give here. But did I remove this part? I put in the wrong place. Sorry, I will exemplify, but later. I will show you an example, but later. This slide is in the wrong place. I will fix this also. Okay, let's continue. So unlike the CNOT, there exists 2 qubit quantum gates with no classical analog. For instance, the controlled phase shift. So now we are going for stuff that doesn't even have parallel, because for now we had this CNOT. There was a parallel in classical computation, was the NOT gate, right? So when it's 1, it gives 0. When it's 0, it gives 1. But now in this case, we can just add a phase shift in one of the states. And in classical computers, we don't have this phase, right? So it means that this controlled phase shift, this gate doesn't have a parallel in classical computers, okay? So the definition is like this. It's diagonal operator, identity in most of the places, but on the last one, it flips it adds phase to the last part here. Okay, so applies a phase shift to the target qubit only when the control qubit is in state 1. Yeah, so this is what it means. So to the control gift, to the control qubit, it maintains everything the same. So this means that this guy here is just identity. And in the second qubit, if the first state is 0, it will just produce the same state. But if the second state is 1, it will add this phase. Okay, so the only guy who will be affected will be 1, 1. So we call this C phase, right? The C phase acting on 1, 1 will be e to I delta. By the way, I'm missing an I here. E to I delta 1, 1. Okay. You can see that a controlled phase shift gate can be performed using C0 gates and single qubit phase shift gates. Yeah. So that's the case here, that we can combine single qubit phase shift gates. So it means that the phase shift will just act on isolated qubits, right? So this guy's only is 1 qubit gates. I will add them, apply them individually. And the C0 gate. So again, C0 gives entanglement, right? So this means that this guy also adds entanglement when you can add entanglement to your system, right? But yeah, you can check this by multiplying these matrices. How do I? Maybe this is too much calculations to do now. But the idea is that you need to make a product of, this is the identity, right? This is the identity. This is the identity. So you will need to do out the product of these two operators and out the product of these two operators, out the product of these two operators. Then you need to multiply these matrices. So the resulting matrix here will be 4 by 4 matrix. You multiply by this matrix, then you multiply by this matrix, then you multiply by this matrix, then you multiply by this matrix. I will not do this case. I will do a simpler one. Maybe if we have more time, I do this. Okay, but it's a lot of multiplications here. So maybe it's too complicated. Okay. There is also this C minus gate. So this is defined like this: is the C phase with phase pi. So we know again that e to I pi, this is -1. This is the most beautiful equation in mathematics, but written in another form, right? So e to I pi plus 1 equals 0. It was chosen to be the most beautiful equation in mathematics. This equation is just, the phase pi will just be -1. So instead of e to I delta here, because delta is pi, we'll just have -1, right? So this gate is important since in some implementation, it is easier to perform C minus rather than C naught. So in some real implementations, sometimes it's trivial to do the C minus. Okay. Yeah, it is possible. It's easy to check the relation between C naught and C minus gates. You just have this Hadamard Hadamard in individual gates. Maybe I can do this one for you guys, so you guys see, right? So if you do a sandwich with Hadamard gates on the C0, remember this is the C0 gate, right? If you do Hadamard C0 Hadamard again, you get the C minus gate. Vice versa also happens. If you do Hadamard C minus and you do Hadamard gate, you will get C naught. Okay, how to do this? So again, I think this one I can do because this is just identity and this is just identity gate. So we are going to do direct product of these two guys. So will be 1 0 0 1 outer product with Hadamard gate 1 over square root of 2 1 1 1 minus 1. Okay, so who is this guy? This will be actually 4 by 4 matrix, right? So we have 1 over square root of 2 times. Then what we do, we put each element of this times this matrix. Will be like this: 1 times 1 1 1 minus 1, 0 times 1 1 1 minus 1, 0 times 1 1 1 minus 1, and minus 1. Oh, sorry. 1 times 1 1 1 minus 1. So this will result in 1 over square root of 2 times bigger matrix 1 1 0 0 1 minus 1 0 0 0 0 1 1 0 0 1 minus 1. So we have to do the product of this matrix times Hadamard gate times C minus, or vice versa. We can do with also with C naught. So let's do maybe this first, whatever. Vice versa. I will just do one to exemplify. So let's do this upper relation. So we are going to do the product with C naught, right? So C naught is 1 0 0 1, and here it was 0 1 1 0. The rest is 0 0 0 0 0 0 0 0 0. I'm sorry guys, but these calculations are indeed very long and boring, to be honest. So 1 over square root of 2, and then you need to do the multiplication of these matrices. Then you multiply again. Let me just put here. I will just I think we don't need to do all this calculation because we're very close to the end. And yeah, so 1 over square root of 2 times again Hadamard gate, right? So this will be 1 1 1 minus 1 0 0 0 0 0 0 0 0 1 1 1 minus 1. You believe me, right? This will be in the end the C minus gate. This will give a diagonal matrix 1 0 0 1 0 1 0 0 0 0 1 0 0 0 0 minus 1. So the product of all these three matrices, we produce this matrix, which is just a C minus. This is C minus. This one here in the middle is C naught matrix. Okay. Now let's go for the Bell basis. It's very interesting. John Bell was this guy who started this, was pioneer, his Nobel Prize. He was pioneer on studying entanglement in quantum mechanics. And this is so-called the Bell basis, okay? So as we have shown, the C0 gate can generate entanglement. In particular, the entangled states of the so-called Bell basis defined by this, okay? So it's a very particular base. Again, these are 4x4 vectors. So in these vectors, you can, using these vectors, it can work as a base for your Hilbert space. It can be a base for your vector space, okay? It's very simple. So it has this phi plus, which is 0, 0 plus 1, 1. Phi minus, which is 0, 0 minus 1, 1. And has psi plus, which is 0, 1, 1, 0. And psi minus, which is 0, 1, 1, 0 with minus, okay? This is the Bell basis. And the Bell basis can be obtained starting from the computational basis by means of this circuit. So we just need this Hadamard gate acting on this qubit, and then we apply the C0 gate. When you do this stuff, you will see that the operational basis results in the Bell basis. So this base here, this base element here, which is not entangled, will result in this base, which is entangled. This vector here, which is not entangled, will result in this vector here, which is entangled, and so on and so forth. And all these guys can be used as a new base for your vector space. This is so-called Bell base. So maybe in the next seminar we can make use of this, okay? Note that this transformation can be inverted simply by running the circuit above from the right to the left, since both C0 and Hadamard gates are self-inversive. Yeah, you remember, right? That if you apply them squared, if you apply this gates squared, they just give the identity. So that's a very good point, that this thing is reversible with respect to the gates. This is why we introduced this auxiliary qubit, because this makes these functions to be reversible. This will be in the future. This will be important. Okay. As a result, any state of the Bell basis is transformed into a separable state. This is possible since we have used the two-qubit gate, right? So previously we had entangled state, but then we can apply this reverse transformation and get a separable state, non-entangled state, right? At this point, it is possible via standard measurement in the computational basis to establish which of the 4 Bell states was present at the beginning. Yeah, so this is mapping, right? So let's say your system came with some kind of unknown state, and after measurement, after you know what was the result, you can predict what was the state that came. So this is, even though we have all this probabilistic character in quantum mechanics, but still there is some deterministic thing. So there are some deterministic elements, and this is what is useful for our calculations. Yeah, okay, so this part of function evaluation, this is a little bit more complicated. It will take me more time to derive this stuff, so I will skip already to conclusions. Next class we start from function evaluations. We will do adding algorithm, and then we go for superconductivity and implementations and so on. Okay, so to conclude, so we reviewed this concept of qubit. We showed the ideas of circuits for quantum computations. We showed single bit quantum gates, right? As the Hadamard and C naught and so on. We studied the concept of quantum entanglement, and this part we didn't do. Abstract and general formal calculating functions with a quantum computer. We'll do this on next seminar. Okay, so I hope to see you guys next week. Thank you all for coming, and I hope to see your home assignments. Okay. All right, guys. Any questions, comments? Okay, so I guess I will see you next week. Thank you. Thanks again for coming. Okay.